These are the key objectives that you can expect to achieve after completing this lesson. Explain the types and sources of measurement errors. Describe the use of measuring devices. Describe the methods for measuring distortion in a welded structure. Identify the types of base metal discontinuities. Measure the dimensions of welds. Describe weld metal discontinuities, measurement methods and acceptance levels. CSAW 178.2, Certification of Welding Inspectors, details the competency requirements for inspectors of welded components. Today, few organizations employ inspectors solely for monitoring and verifying welding operations. In addition to these activities, an inspector might also be required to check incoming material, measure its thickness, check the size and location of bolt holes, measure dimensions of welded shapes, and so forth. Thus, the inspector must have a broad range of skills and knowledge to make an effective contribution to the operations of the shop. The most important instrument to consider is the human eye. For visual examination to be meaningful, it is essential that the eye be well trained and functioning properly. As for any measuring instrument, checks at regular intervals should be carried out and any deficiencies corrected. Vision requirements are specified in CSAW 178.2, Certification of Welding Inspectors. Many inspection tasks involve measuring something, and many of them involve measuring a length. This may be the size of a fillet weld, the width of a gap, or the distortion in a welded product. Regardless of the type of measurement, there are a few basic ideas that should be understood by the inspector. First, consider the difference between accuracy and precision of a measurement. Accuracy is how close repeated measurements are to the true value. Precision is how close repeated values are to each other. The figure illustrates the difference between accuracy and precision. You can see it is quite possible to make very precise measurements that are quite inaccurate. Precision depends, to a large extent, on the instrument used for the measurement. A micrometer, for example, has much greater precision in measuring length than a steel rule. The inspector must select a tool that has adequate precision for the intended measurement. A simple method for improving the precision of measuring scales is the vernier. This was invented in 1631 and, although used mainly on such instruments as calipers, micrometers, and height gauges, it is also found on dials, protractors, or similar instruments that use a scale. Modern instruments often have digital readouts with 4 or 5 significant digits displayed as shown in the top figure. This gives the impression of a highly accurate instrument, but, again, high precision does not mean high accuracy. The first step on measuring with a vernier scale is to zero the tool. This, however, is not calibration. As with all measuring devices, make sure the surfaces are clean and in good shape. This simple device increases the precision of measuring instruments. A 10-division vernier scale is shown. The second scale has 10 divisions that occupy the same space as 9 divisions on the main scale. There are 2 types of errors. First, there is the general scatter among the cluster points themselves. This is a random error. Then there is the shift of the whole cluster from the center of the target. This is a systematic error. Systematic errors are very serious because they can be repeated with every measurement and you might not know they are there. For example, suppose there is an error in the position of holes on a drilling template used for locating bolt holes on a structure. Every time the template is used, the error is transferred to the component. The tolerance is the difference between the highest and lowest value that a dimension is allowed to have. If it is outside the limits, it is unacceptable. For example, CSAW 59 gives the tolerance on the depth of welded built-up beams as plus or minus 3 mm for depths not exceeding 900 mm. This tolerance is relative to the specific depth. Thus, for a specified depth of 550 mm, The upper and lower limits are 553 and 547 mm respectively, and a depth outside these limits would be unacceptable. In many cases, limit gauges can be used to establish the acceptability of a dimension using the go, no-go approach, which avoids having to measure the actual dimension. A limit gauge is shown in the figure. To be within tolerance, the bar must fit in the go end, set at the upper limit, but not fit in the no-go end, set at the lower limit. This saves time but does not provide any information on what is being achieved. Information is becoming increasingly important with the use of modern statistical process control methods. In statistical process control, actual measurements are made on the product and analyzed. Even though a product may be within specification, such information tells whether the process is under control. For example, tracking the actual values achieved in a product may indicate whether the process is going out of control before any components are actually rejected. To ensure accuracy in a measurement, the instrument must be properly calibrated and the measuring technique must strive to minimize errors. Calibration procedures vary according to the instrument or measuring device but are all based on the idea of calibration against a traceable standard. That is, the device must be calibrated against another device, which is itself calibrated against a standard. Eventually all calibration can be traced through to a national standard. Calibration intervals should be established as part of the formal calibration program. These might be based on importance, frequency of use, or type of instrument. Calibration records should be available that show when an instrument was last calibrated. Calibration should only be done following the correct procedures and minor adjusting or fiddling with an instrument should be avoided. For example, setting the zero on an ammeter does not calibrate it. It only sets the zero and the meter could still be inaccurate in the range to be measured, let's say at 400 amps. When reading meters with needles, always stand directly in front of the meter to read it. Standing at the side may introduce a parallax error because the needle is displayed slightly away from the scale as shown in the figure. High-quality meters often have a mirror in the scale that allows you to line up the needle with its reflection before you take a reading. Dimensions should be measured from a common datum or reference line as specified in the drawings. This avoids the risk of cumulative errors. A cumulative error can be illustrated by considering 5 holes that are to be drilled 100 mm apart in a straight line. The position of each hole has a tolerance of plus or minus 1 mm. If the location of each hole is measured from the preceding hole, then the previous error is added to the tolerance. That is, there is a cumulative error. The 5th hole could actually have an error of plus or minus 5 mm. When all hole positions are measured with respect to a single edge, then each hole is subject to the same error of plus or minus 1 mm. Be aware of what lines are specified on the drawings as datum or reference lines. There could be several depending on the structure. Use of the correct reference line is critical, for example, in determining the location of a nozzle in a vessel. An example of a datum line in a drawing is shown. As the changeover from imperial to SI units progresses in North America, you may be required to work in either set of units. Some codes and standards are available in both systems. However, stick to the system specified for the job and use instruments calibrated in those units. Avoid measuring in one system and converting. Standards such as CSAW 59 are published as a metric system and show imperial as a reference only. They are not exact conversions. For example, the allowable root opening for a fillet weld is 2 mm or 1/16 inch. These are not the same. 2 mm is actually 26% larger than 1/16 inch. Therefore, be certain you are always working to the correct units of a code or standard. Care of inspection tools is an essential part of the inspector's job. Avoid dropping or striking tools, which could cause burrs, kinks, or other mechanical damage. Check tools frequently for wear and proper adjustment. After use, wipe them clean with a suitable cleaning fluid, dry them and then wipe with a slightly oiled chamois or cloth to prevent corrosion. Measuring tools should be stored where they will not be damaged from damp, dust or impact. For measuring dimensions greater than about 1 meter, the steel tape is the most widely used measuring tool. A tape cannot be calibrated in the sense of adjusting it, but it can be checked against a standard and should be maintained in good working order. The standard recognized temperature for checking steel tapes is 20 degrees Celsius, 68 degrees Fahrenheit. Tapes usually have a hook or similar device at the end to hook over an edge which serves as the datum. Ensure this is not worn, damaged, or altered in any way and check that it does not introduce any zero error in the readings. For accurate measurement, long steel tapes should be used under proper tension. The correct tension for a particular tape is sometimes embossed on the tape blade near the beginning. If you find the markings 20 degrees Celsius, 70 N, then the tape was designed to be accurate at 20 degrees Celsius with a tension of 70 newtons or 7.0 kilogram force. Standard tension for most long steel tapes when fully supported throughout their entire length is shown. A tension handle with a tape clamp is attached to the end of the tape and correct tension is applied. Roll over the images to see how the tools are used. Support of a tape for long dimensions is important since sag will cause an error and result in the dimension being overestimated. A pot magnet or a small G-clamp is useful to secure one end of the tape when the inspector is working alone. If you make measurements outside in the cold, allow the tape to adjust to the temperature for 15 to 20 minutes or use a tape that is stored outside. The tape in the structure will then be at the same temperature. Shorter dimensions can conveniently be measured with a steel rule. Ensure the ruler is at 90 degrees to the edge or 90 degrees to the surface when making a depth measurement. The zero of the scale on a steel rule is at the end of the rule unlike wooden rulers. It is important the end is not worn or damaged. When measuring from the edge of a component, use a small flat block to establish the reference datum line rather than guess the zero portion. Straight edges are used as reference lines and are useful for measuring distortion and flatness of welded components. Vertical reference lines are easily set up using a plumb line. Both horizontal and vertical planes can be checked with a spirit level. A most useful tool is the combination square, which is valuable for checking 45-degree preparations, checking squareness, repeating measurements, and using as a straight edge. Most combination squares contain a built-in spirit level and scriber. The fundamental instrument for checking squareness, 90-degree angles, is the steel square, consisting of a large arm and a smaller one which meet at an angle of 90 degrees. On the steel square, the wider arm is called the blade and the narrower arm is called the tongue. Precision steel squares are referred to as machinist squares, and consist of a steel blade inserted and either welded or pinned into a heavier body at an angle of 90 degrees. Both the inside edge, as shown in the figure on the left, and the outside edge of the square can be used. A typical application would be checking the angle between two plates fillet welded together, as shown in the figure on the right. Note that for such uses, the corner of the square is clipped to clear the fillet weld as shown in the figure. If a square is modified in any way or if it has been dropped, it must be checked before trusting its accuracy. If it is not convenient to place the square directly against the vertical member, then gauge blocks, feeler gauges or a rule can be used to take measurements at two locations as shown in the figure. If the measurements are the same, the angle is 90 degrees. Steel squares should be treated with care to avoid damage or distortion and should be checked regularly for squareness. A simple method of doing this is to place the square against the plate edge in position A, and scribe a line. then move it to position B to check if the line is at right angles to the plate edge. This method is quite sensitive as any error is doubled, and it requires a good straight edge on the plate. The figure illustrates other methods for checking squareness that do not require a reference edge. A string may sometimes be used to set up a reference line, for example, when measuring warpage in a plate. Measurements must be made in the horizontal direction so that they are at right angles to the sag in the string to avoid errors. An error will be introduced into the dimension if a measurement in the vertical direction is made. The figure shows a method for measuring warpage in a plate. The string is run over two blocks of equal height, labeled A in the figure, so that the string clears all high spots. Measurements are then made of the inward or outward warpage or bulge using the string as a reference and allowing for the thickness of the blocks. There are a variety of 1, 2 and 3-dimensional systems with different levels of sensitivity and measurement capabilities available. They range from a single visible line to rotary laser levels that produce a level laser line 360 degrees around a workspace. Using a laser that is made for outdoor exterior work will require a laser detector since the laser beams cannot usually be seen by the human eye in bright conditions. In addition, detectors generally increase the distance that a beam can be used. Laser level and alignment systems can check large areas for flatness and straightness and can measure if they are square. They can be used to measure alignment during fit-up, calibration of jigs and fixtures for manufacturing, and distortion caused by welding and/or heat treating. Straightness measurements are performed on a large number of applications, for example rolls, machine construction, and transportation lines. Gaps can be measured with feeler gauges or graduated tapered wedges. Feeler gauges measure the narrowest point of the gap, whereas the wedge usually measures the gap at the outside edge. Larger gaps or inside dimensions can be measured with calipers. The calipers are transferred to a rule to obtain the dimension using a flat block as a datum, as shown in the figure. Outside calipers may be useful for measuring thickness, for example, at a weld, but only if the calipers can be removed without moving the caliper joint. Angles, such as weld preparation groove angles, are measured with a protractor either by using the protractor directly on the workpiece or by setting the angle on a bevel gauge and transferring it to a protractor to read the value. Small dimensions where high precision is required are measured with a micrometer. Micrometers are precise, delicate instruments that should be treated with great care. Wipe the faces and the workpiece clean before making a measurement. Do not use excessive measuring pressure, 2 clicks of the ratchet are enough, and do not leave the faces in contact when not in use. Calibration of a micrometer, either vernier or digital, involves checking the zero error by cleaning the faces, closing up the faces, and observing the reading. If this is not zero, the instrument can be adjusted to remove the zero error. The instrument can then be checked with gauge blocks of various thicknesses to determine if it is accurate over the rest of the range. Gauge blocks and tool should be at 20 degrees Celsius, 68 degrees Fahrenheit, during calibration. The inspector may be required to measure temperature, for example, the preheat temperature of a plate before welding commences. The most convenient method is the thermocrayon, often called by the popular trade name, temporal stick. Each crayon is graduated to a specific temperature. To use, mark the heated plate with the crayon. If the plate has a temperature higher than that indicated on the crayon, the mark will smear as the crayon material melts. Make sure the crayon is not directly exposed to the preheating flame. To establish the temperature of the plate, you may need several crayons covering a range of temperatures to find the highest one that just melts. In many cases, the exact temperature is not required and only 2 crayons corresponding to the minimum and maximum temperature specified are needed. Infrared thermometers can be used to check preheat, interpass and post-heat temperatures. Most of these instruments do not take a spot temperature reading. There is beam spread. The farther you are from the surface you are measuring, the larger the area is that is being measured. Read and follow the manufacturer's operating manual so you get accurate temperature measurements. Where preheats are concerned, you must take care to measure the temperature at the correct location. CSAW 59 states that the surfaces of the parts on which weld metal is to be deposited must be at, or above, the specified minimum preheat temperature for a distance equal to the thickness of the part being welded, but not less than 75 mm, both laterally and in advance of welding. This is shown in the figure. The specified minimum preheat must be achieved prior to starting to weld and must be maintained during welding. You have completed this lesson and you should be able to explain the types and sources of measurement errors, describe the use of measuring devices, describe the methods for measuring distortion in a welded structure, identify the types of base metal discontinuities, measure the dimensions of welds, describe weld metal discontinuities, measurement methods and acceptance levels. Congratulations! You have completed this lesson. Click the replay button to begin this lesson.